All right, so hopefully your quick quiz went well, and you're ready to kind of move on here to the new stuff for today. So you should have gotten a set of notes from the sub, and so today we're going to be talking about some more transformations on trig functions. So I do have a worksheet to sort of go along with that for over the weekend, but let's get started with the notes. So you may recall in the last class we talked about parent functions for all three of our basic trig ratios, sine, cosine, and tangent. And then we also applied some transformations onto those, being horizontal translations and vertical translations. The horizontal we call the phase shift. So today we're going to focus on scale changes. And most often we talk about scale changes, particularly when we're talking about sines and cosines. We have different names for those. Our horizontal scale change is related to the period, and the amplitude is related to a vertical scale change. The period goes with the horizontal scale change that controls how often the curve will start repeating itself, and the amplitude tells us how high and how low it's going to go. That would be a vertical scale change. So amplitude's pretty easy. We just take the number that's multiplied out in front of the trig function. For example, if we take this, look at this function y equals 3 cosine x, all we're really going to do is just stretch everything by a factor of 3 from that baseline, which for today is just going to be the x-axis, but later on it will be different places. If we're graphing the function y equals 1/2 x squared, then all we need to do is just stretch those y values by a factor of 1/2, which is really compressing it. We're making all those y values 1/2 of what they were before in the parent function. So amplitude's pretty easy. Period is a little bit more going on here, and also a little bit different depending on whether we're talking about tangents or sines and cosines. So let's start a little bit just thinking about sines and cosines. Those are the easier ones. So recall from last year that the period of a function, particular for sines and cosines, is equal to 2 pi times the reciprocal of b. So b, draw that very well, looks like an 8. Try it again. There, might get a little bit better. So b is whatever this number happens to be. Whatever that number is that's multiplied out in front of the x, that's our b value. So if we're graphing that one, then find the period, we essentially just take 2 pi, which is the base period for a cosine function. That's what we're working with. And we're going to multiply it by the reciprocal of b, which in this case is just 1/2. So the period for this one would actually be pi. Tangent is a little bit different, and we'll get to that in just a few minutes. So that's pretty much it. We can go to the first example here. Let's kind of just figure out what's going on with this one. You'll immediately notice that what's different about today as opposed to yesterday's. Yesterday we looked at adding and subtracting numbers to the x's and to the y's, and so what effect that has is that it just slides the graph around the coordinate plane. This one, since we're working exclusively with multiplication, is going to work a little bit differently. In this case, the phase shift, we're not actually going to have one, and there will be no vertical shift either. That's because nothing's being added or subtracted anywhere in that function. The amplitude, pretty easy. That's just going to be the 3. That's the multiplier that's out in front. Whatever number you see there is exactly what happens. Now the period, remember our formula here for sines and cosines is going to be 2 pi times the reciprocal of the number that's there. We did this already. So our period here is going to be pi. And then we'll kind of work with the domain and range here in a few minutes, but so that's pretty much all we need to get a graph of this thing. I'm going to go back to the parent function. So this one is a cosine function. The parent function that we did during the last class looked like this. And remember we talked about this idea of just having those 5 key points within one cycle. That cycle will just repeat itself, and so what we really need to do is create something that looks like this just with those scale changes kind of put together. Now we'll notice here that, we're in a different color, notice that since we're working with a cosine, the very first number is not actually at the origin, it's 1 unit above. So ours is actually going to be a little bit different. We'll get to that in just a minute. Let's get the period started on this one. All right, so let's work with period first. So as I said in that last one, the parent function, we would start at 0, 1, but since I've had an amplitude of 3, that means I'm going to start that point, which was here, is actually going to get stretched by a factor of 3 away from that baseline, or in this case, the x-axis. So our first point on this is actually going to be at 0, 3. We'll go ahead and write that down here. And since our period is pi, we're going to make a scale here. This is going to be at pi, 2 pi, and maybe 3 pi. So since the period is pi, that means this thing is going to complete a cycle in, in pi units. So since this is going to be a peak of the curve, the one point that we have here, there's going to be another peak at pi 0, and that's going to be kind of the end of that cycle of 5 points. Going back to this parent function we talked about the other day, we noticed that kind of halfway between here and here, we have where it bottoms out. So we'll go back and do that for this one. So halfway between the 2 points that we have is going to be here, but we're going to drop that. That's going to be where it bottoms out. And again, we're going to be at -3, since that's going to be the amplitude of our graph. Halfway between those points is where it's going to cross our baseline on both sides, and so we end up with this. So let's get those points in there before I forget. This one is going to be pi over 2 and -3. I just realized I goofed up here, sorry. That's going to be at pi 3, not at 0. This point over here is going to give us, would that be pi over 2? We got pi over 4 and 0. This point here is going to give us 3 pi over 4 and 0. And again, that's going to be halfway between this pi over 2 and the 2 pi. Or this, yeah, sorry, this one's at pi. Pi over 2 and pi. Okay, so let me try to get rid of those without destroying everything here. Let's see, I'll put that. Oh, shoot. Let's try this. There we go. All right, so that's our 5 base points. And so once we have that, then we can just kind of keep repeating this. These peaks are going to continue every pi units away. These are going to be repeating every pi, so on and so forth. So we'll just throw in some extra points there just for a little bit of variety. Make sure when we complete this graph that we make it nice and smooth curves. We don't want this to look like an absolute value function that just has all these little pointy line segments. So put a little bit of curvature in there because that's the way the sine curve is going to look. Once we have that in place, then our domain, which would be true for all sines and cosines, is going to be from -infinity to +infinity. Our range for this one is going to be a little bit different because we're actually stretching those vertical values. And so you notice on the graph here that we're going to go from -3 to +3. And that pretty much does it for this one. So again, you can look back at this, take some notes, replay parts of it if I was going a little bit too fast. It's one of the benefits of having the video as opposed to me just being in class, is that you can kind of replay what I said. Hopefully it makes sense. And if it doesn't, I'll be back. Be back tomorrow or next class. You can ask questions then. All right, so let's go to the next one on the back. And so this one is a tangent function. This is going to be a little bit different. It'll probably take us just a little bit longer to kind of talk through some of the little idiosyncrasies for our tangent graphs. So, basic thing here, we don't, basic idea here is we still don't really have anything being added or subtracted here. So we're not going to have any phase shifts. We're not going to have any vertical shifts. We will have amplitude. Actually, we won't have amplitude. So when we talk about tangents, we don't really have amplitude. We call those a vertical scale change. So I'll just call it a vertical scale change. Amplitude really refers to the wave pattern that we get with sines and cosines. And again, we don't really have that for this one. But pretty much it's going to work the same way as an amplitude does. All this does is tells us how much the scale change is going to be. These y coordinates are going to be stretched by a factor of 2 in this case, a factor of 2 away from that baseline. Our period here, we're going to have to go back and kind of talk a little bit and make some addendums here to the front side. So go ahead and turn back to the front side. So I said this one for sines and cosines was 2 pi times the reciprocal of v, or multiplied by 1b. And that's because this guy right here, this 2 pi, is actually the period for a parent function for sines and cosines. Now you may recall from yesterday's class that when we talk about tangent functions, those actually have a period of pi. And so we have to adjust our formula a little bit because our parent function looks a little bit different. And so for tangents, let's find some place to put this here. Okay, so for tangents, we start with the period for the parent function, which is just pi, times the reciprocal of that multiplier that's with the x, times 1 over b. Okay, so those formulas are just a little bit different. And again, the big idea there is that with the parent function, we have different period with the parent, right? The parent function only has a period of pi units, so we have to adjust the formula just a little bit. And so we'll see that real quick just to kind of go back to the tangent parent graph from yesterday. We noticed that the period here was repeating every pi units, so that's why we have to make an adjustment to that formula. Okay, so just small little hitch there. Make sure you keep track of that. And so here, back to our problem here. So our work here is going to be that our period is going to be pi, which is again the period for the parent function, times the reciprocal of that 1/3 in this case. Okay, so reciprocal of 1/3 is 3, and so our period in this case is going to be 3 pi, meaning that we're just going to be repeating every 3 pi units. The vertical asymptotes are going to be 3 pi units apart from each other. So that's pretty much the idea there, and so that's our period. We'll go put that guy right there. All right, so let's go back to our parent function and just kind of make the connection to those. So again, you may recall from last class that our tangent function actually starts right smack in the middle at the origin, and since we haven't had any translations to this, then that's going to be the case for this graph that we're looking at in your note set. So we're going to put one right at the origin, just like the parent function has. It's going to be there. Go back to the parent function from the other day. And what we'll note here is that there's symmetry here, mainly that between that origin point that we just had and the distance to this is just half of the period. And the full period actually gets split up over these two sides. We'll note again that this other point up here is halfway between the origin point and the vertical asymptote. So from that origin point, we're just going to go horizontally. We're going to go halfway to the vertical asymptote, as we did here with the parent function. And in this case, this next point, I think I'm getting ahead of myself here just a little bit. So let's get the vertical asymptote set in place first. So we're going to just kind of split that period between the two sides. So here I'm going to have, let's see, let's just go 3 pi, let's see. So we're going to want 3 pi. That's going to be split over these two sides. So let's make that, we'll put one here at 3 pi over 2. So each one of these hatch marks on the x-axis is going to be a pi over 2 scale. And we're going to do the same thing over here. We'll go 3 that way. Put ourselves a nice vertical asymptote at -3 pi over 2. And collectively, that gives us 3 pi altogether. We'll go, maybe let's put a couple more of these in here. We'll go 1, 2, 3, 4, 5, 6 here. And so that's going to give us 3 pi more on top of that. So that would be 3 pi is what? 6 pi over 2. So here I have 9 pi over 2. So get a couple of those in there just to kind of show how it repeats. All right, so we kind of have that in place. So now we just need to put the other points in here. Again, we'll go back to the parent function. And our parent function here, we went halfway between here, that origin point, and the asymptote. So we went over halfway, and then we went up 1 unit there. Okay, so that's always the case. You're always going to go halfway to the asymptote, and then you're going to go up by 1 for the parent function. But since our points, remember, have been stretched by 2, it is 2, right? Yeah, I've been stretched by a factor of 2, then our basic idea for that one is that instead of that point having a y value of 1, it's just going to be 2. It's stretching all the y values by that scale factor. So let's go back and put that in here. So we're going to go halfway to our vertical asymptote to the right, and we're going to go up 2. Right, and that one is going to have kind of an interesting coordinate point because remember this one is pi over 2. That's our scale here. And this one is going to be at just pi. This one is at 3 pi over 2. So we got a little bit of work to do with our fractions here. So halfway between pi over 2 and pi is going to be 3/4 pi. 1/2 pi to 1 pi is 3/4 pi. So I'm going to get that point down here written down before we forget about it. So that's 3/4 pi. That's going to have a y coordinate of 2. And likewise, we can do that in the other direction going to the left. We're going to go halfway to the distance here to the asymptote. That's going to put us at -3/4, and then we're going to go down 2. We're going to get this point. So I'm going to put that here, -3/4 pi, or 3 pi over 4, and -2. And then, of course, the point that we had at the origin, which is just 0, 0. And when I complete that cycle, that's what I get. And then, of course, because that just repeats, I can just keep kind of doing that pattern. Let's do one more of them. I always like to see at least a couple cycles of this. Okay, we don't have to get those in the exact place, but we can go ahead and name those coordinate points then too. This will be a little bit trickier here. So what do we have here? So we've got 3 pi over 2 and 9 pi over 2. Halfway between that is going to be 6 pi over 2, also known as 3 pi. And so let's go ahead and put that in here. That's our middle point for this next set, 3 pi, 0. I'm going to go from 3 pi, or 6 pi over 2, to 9 pi. Have some space in there to do that. So why don't we, I think just because of the complication of kind of what our fractions are looking like here, let's just kind of leave that on the back burner here for just a second. And let's just suffice to say that when we do tangents, we'll work on this a little bit more probably on Monday. We'll take a look at these a little bit more closely. But as long as we get that first set down, I think we're going to be in good shape, and we'll kind of get into more complicated fractions maybe on Monday when we can talk about it together. So good for that first set. Make sure you actually just draw the second set. We don't have to name those right now. And then we'll kind of go in and just look at our domain and range. The range, again, is always easy for these. The range is going to be from -infinity to infinity. And then our domain, in this case, is going to be a little bit more work to do for this. And again, we talked about in class the other day how we have these repeating vertical asymptotes. Remember that the domain is all values of x that I can plug in and get something out. So there are clearly some numbers on here that I'm not going to be able to plug in for x, which is why they're not showing up as points on the graph. So we just want to kind of work on defining those a little bit more clearly as to what those are. And let's see. So our domain here, let's bring it down here. I think we're running out of space. Our domain then, the first restriction here really is this 3 pi over 2. So we're going to start by saying that x cannot be equal to 3 pi over 2 plus or minus, and then this is where our period comes in because we're going to see that those are going to repeat every 3 pi units. We're going to have one of those vertical asymptotes. So we're going to say the first value here is at 3 pi over 2 plus or minus that period, and then any whole number multiple of that period, we're just going to call that k. So it could be 3 pi times 2, or 3 pi times 4, 3 pi times -2 if we want to go backwards in the negative direction, but that pretty much is going to do it for us. The other thing is we want to make sure that we put that k is an integer, or we can also say that k is contained in the set of integer values like this. This is a little bit more fancy notation for it. Either of those is fine for me, depending on how you want to do that. You don't have to do both, just one. So we'll put an or sign there. All right, so this is our tangent graph for this one. Again, tangents can be a little bit trickier at first, but I think as we get into more complicated ones, when we start putting translations and scale changes together, I think they end up being just a little bit easier. But we'll get to that later on. So I hope the video went well for you. Again, I'll be back to school on Monday if you have any questions about things, and we'll make some more progress with things, and we'll kind of put everything together and just spend a couple days working on some functions that do have translations as well as scale changes. Okay, well, thank you.